Welcome back everyone, Item is here. In this video I will be trying to explain how eProgram is run into your computer. In this video we'll be diving a little deep into um, some details or some code in the operating system itself, which is the kernel. We'll be trying to reference some kernel code. So far I think we have covered how CPU execute machine code loaded from executables, what are the different kind of security rings we have, how syscall is working, what is the difference between user space and kernel space. So we will be using all that knowledge just to explain now how eProgram is working exactly. So in this section or in this video, I will be trying just to dive deep into the Linux kernel just to figure out how programs are loaded and run in the first place. So I'm going specifically to look in the Linux 8664. Why I'm going to use the 8664? Well, eventually because the Linux is a fully featured production operating system for desktop, mobile, and servers. So Linux is a quite good candidate just for researching. So because it's an open source too, and it's super easy just to research just by reading its source code. And I will be directly just referencing, as you can see, the code from the kernel from the GitHub. Yeah. So we will be using the architecture 8664 because that most of the computers now, or most of the modern desktop computers, are using this architecture as a target. So the subset of behavior I will be mentioning that is all specific to the 8664. So most of what we will be trying to learn in this video will generalize well the other like operating systems and architectures, even like if they differ in various specific ways. So we will be starting with something called a syscall or an exec syscall specifically. So we'll be talking a little about this exec syscall. So just to imagine a little, I will be trying to just try to draw a diagram that can explain well what is happening just using an exec syscall, and then we will be trying just to dive more into the kernel code. So we have a user space. Um, Actually, and we have a kernel space too. Kernel space. This is the kernel space. Um, Let me just throw a bigger rectangle. Not so bad at drawing. Yeah. So this is the user space. So when we try, for example, to run this in the Linux, which is, for example, a dot slash, for example, file dot bin, we are actually calling the execve actually. So the execve that we will be trying to research later on um, is going to call that file. Sorry for the bad drawing. Okay. Um, and etc. I think we'll be trying to see the other arguments, and then it will be doing a syscall instruction underneath. That will be taking us to the kernel space, which will be um, setting or loading the binary for us, loading and just doing some loading and some setup for the binary. And then it will be trying just and the kernel eventually will be trying to just figuring out the binary format of that specific binary. So it will be just trying to identify the binary format of that specific binary that is that the exec VE is trying to run. So and if it's identified, then it's going to start a new process, and we will be talking more about that. Otherwise, if it's a no, it's going to repeat the same thing. She's just trying again the binary format, just trying again to figure out the binary format um, of the binary. So sorry for the bad drawing, but this is basically what is happening. So you have a user space. So the program before just being run is just calling the execve, and the execve is going to do a syscall instruction that will be switching the CPU from user mode to kernel mode, and then in the kernel space it's going to start executing the operating system code, or specifically the kernel code, which will be trying to load and set up the binary for you, and then it will be trying some binary formats, just a loop. Just let's imagine it as a loop that will be going until it tries to find out the format of the binary. So each binary has its own format. So for example, Windows has its own formats, which is the PE, which is a portable executable, and the Linux has a format called the ELF, which is executable linkable file. So this is the kind of two pretty like famous formats that you can have for binaries. So we will be trying to work more on the ELF actually, and I will be trying to dedicate a video for the ELF too, as the assembly language as the other videos that I said I will be making. So let's just start with a very important system call, which is the execve. So actually it loads a program, and if it's successful it replaces the current process like with that program. So a couple other syscall, like for example the exec LP, the exec VPU, you just VPE, I'm sorry, you just they are existing, but like they are all layers just on the top of the exec VE, so in various fashions. So um just there is a little just curiosity that I have been having. What does the VE means exactly? What does this VE mean? So I have um I have been in the internet. I tried to research that, and the v is actually means one parameter is the vector list of argument, which is the argv, and the e means like just another parameter in the vector of environment variables. And various other execs calls like have different suffixes just to designate different code signatures. Um, yes, this is basically what the v and the e are just having. So let's try to look at the signature of the exec VE. Just from the man page, or the Linux manual page. So the exec VE is pretty like function like any other C functions. So it has a pointer that points to a string, which is the path name, another pointer to the argument vector, which is actually an array, and another one for the EMVP. So let's try to break down each one of them. So the path name is actually an argument that specifies the path to the program to run. And the argument vector is a null terminated, just meaning the last item is a null pointer, or a list of arguments just to the program. Like the argument C, for example, argument you will commonly see passed to the C function, to any C, to any kind of C, uh, not like specifically any kind of C function, but specifically to the main, yeah. So when it's passed to the main function, it's actually calculated just later on by the syscall. So this is why there is a null termination. So the EMVP, which is just an argument that contains another null terminated list of environment variables used as the context just for the application. So they are conventionally, I think, just in the format of um, key value or something. They are in the format of key value like that. This is for the EMVP. Yeah, so just if in fact, like, you know that conventions where a program first argument is the name of the program itself, well, it seems out that's purely a convention and it isn't set by the execve syscall itself, and the first argument will be whatever is passed to the execve as the first item in the argument vector argument. So even if it has nothing to do with the program name. So interestingly, like the execve does have like some code that assumes, for example, that the argument vector of zero, is actually the program name is actually the program name. And more on this later on. We will try just to walk more about the interpreted scripting languages we will be trying to see at the end of the video. Um, let's start by just doing some definitions, which is like for us like the step zero just to define stuff. So we've already just know how syscall works in the previous video, but we've never seen a real world code example like. So for example, look. Um, at the Linux kernel source code and see how the exec VE um, is defined under the hood. So the first thing that you can define is that you can look, I'm sorry, is the syscall define 3. So this is called a macro and it is just for defining a 3 argument system call code. So I was like curious, why is the 3 hard coded in the name of this syscall? And it seems out that just after googling that around, I just learned that this was a workaround just to fix some security vulnerabilities, so that's why they add 3. Well, another interesting thing that you can look at. Those are the parameters, and this is the return. Actually, the return is another function called the do execve, which takes, for example, it has a function which is the get name, and the file name, and the argument vector, and the emvp. So the file name argument is passed to a get name function, which copies the string from user space to kernel space, and does some usage tracking things. So it returns, I think, a file name struct that we will be trying to see later on, just which is defined in, for example, in here, which is in the file system dot h. So um, it's actually a kind of structure which stores a pointer to the original string user, as you can see, the original string user, and it has also a new pointer to the value copied to the kernel space. So this is the original userland pointer, which points to the string of the original file name, and this is a string or a pointer that points to the string in the kernel space. I think this is really interesting. This is pretty good as like code. Like I think Linux Torvald, the one who coded that, is it's really interesting. So the execve system call then calls a do execve function. So this is the do execve function that we talked about. So this is in turn calls just the do exec ve at common, and the code is in here basically. So this is the do exec ve. So like with some defaults, it's going to call another function which is the do exec ve at common. Is accessed with some defaults as the other one. She's at the fd cwd. Will be trying to see that, and the file name and the argument vector and the emvp and the zero again. So the exec ve at actually um syscall, which is a syscall actually that I have mentioned earlier. And I think also we have a do execve at common, which is another function that we have to look at. What do we have also? Yeah. So I think until now it's a kind of chain of a lot of an exec VE. So just to reach more about what is happening, maybe it is just time to look more at the exact VE add and then go back and try to see if we can see the exact VE add command. Yeah. So, for example, in the exec VE add, which is this one, a file descriptor or a type of ID, I think that points to just some resource is passed to the syscall, and then there is a do exec ve add command. So I think this specifies just the directory to execute the program relative to, and the exec ve itself. I think there is a special value is used, which is that. This value is actually used for the file descriptor argument. Um, for example, this is just a shared constant, I think, in the Linux kernel that tells the function to interpret path names, for example, as relative to the current working directory, and functions, for example, that accept file descriptors usually include a manual check. For example, I don't know, there might be just an if the file descriptors is equal to that, then it's going to go into some special to some special code or some special other code. This is actually what I have understand from the whole thing. So yeah. Now the next setup just um, to do is we have now just reached to do exec ve at common, which is the core function handling the program execution. So we are going now to take a brief step back, just relax down, just and stop just staring at the code and just to get a bigger picture view of what this function does. So the first major job after just researching on the internet, the exec ve at common is setting up a struct called the Linux bin param. So I won't be just including a whole copy, but we can just look into that. For example, uh, in the internet, Linux param, Linux bin param, yeah, GitHub struct. You can just look at it if you want. Linux bin format. Let's say Linux bin param. This is not the one. Is there any kind of okay? Yeah. Okay. This is the Linux bin param. Yes, this is the one. So, but like when you look at the Linux bin param, there are several like important fields that I want to go over, which are, for example, the struct, which is this one, and there's also the VM like area, which is what is it? 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 The VM area. The VM. Yeah, I think it's like the VM area. Is it not here? Let me just check that out. Yeah, never mind. Okay, so the data structures like the struct that is in here, and the VM area struct, which is I don't know what it's not why it's not defined in here, is actually defined just to prepare the virtual memory management like for the new program. So, for example, the argument count and the EMVC are calculated and stored to be passed to the program. And for example, the file name and the interrupt store the file name of the program and its interpreter respectively. So this starts out equal to each other but can change. For example, in some cases, one such case is when running interpreter scripts with a shebang. For example, when executing a Python program. So, for example, file name points to the source file, but interrupt um, is the path to the Python interpreter. So the buffer also, which is another interesting thing, is an array filled, for example, with the first 256 bytes of the file to be executed just because it's used to detect the format of the file and load script shebangs. So the bin stands for binary program. So just by taking, for example, um, just for by taking just a closer look at this buffer, we can look at it in here. This is the buffer. As you can see, its length is defined as um, the constant bin param buffer size. By searching the code base just for the string, we can find a definition for this, for example, in this one too, which is the U API, which is the user API. Um, so the kernel just loads the opening of 256 bytes of the executed file just into this memory buffer. So just an aside story, the UAPI um, is actually stands for the user space API. So in this case, it means someone decided that the length, for example, of the buffer should be part of the kernel public API. So in theory, I think everything in the UAPI is exposed to user land, and everything non-UAPI is private to the kernel code. So kernel and user space code, I think, originally just coexisted in one thing, and I don't remember when exactly, but I think in the 2012 the user API code was refactored just into separate directly. I think it was refactored into separate directly. Yeah. So just I think it was an attempt just to maintain or to improve the maintainability or something like that. Yeah. So I think this is all about now what is happening inside the execve. So now another step is going to just check out the formats of the binary itself. So this is where the kernel next major job is going to iterate. Is he's going to do a bunch of binary formats handlers. These handlers actually can be just defined in the, for example, in the file system bin formats lfc. I can just look at that. For example, I don't remember that exactly, but I think it is in that file. Formats. Is it elf? Yeah, I think elf. Yeah. The C Linux. I think this is the file that contains. Yeah, this is the file. So the whole binary formats checks are loaded using um, or iterating or using this file basically. So um for example, each handler will be exposing a load binary, so a handler is going to help us check the binary formats um of any binary that will be given to the kernel. So there will be so there will be a load binary for each handler function that will be taking a Linux bin param structure. um, and then it will be checking if the handler understands the program format. So this often involves looking for magic numbers so in the buffer, so attempting just to decode the start of the program also from the buffer. And magic numbers, guys, are a kind of something that we can use just to identify a binary or something. So and before we check the file extension and all of that, so for example, if the handler does support, I don't know, the format, it prepares the program for execution, and just returns a success code or something. Otherwise, I think it's quite just early, just returns an error code. So if it does not like try, and try again to find out the binary format of that or the format of that binary, uh, I think eventually it will quit and just returns an error code. So the kernel tries, for example, the load binary function of each binary formats until, for example, it reaches one that succeeds It means that, okay, he identifies that binary as that and as that, as that, etc. So sometimes this will run like recursively. So for example, if a script has an interpreter specified and that interpreter is itself a script to, I don't know, the hierarchy, like might be something like that. I don't know, it might be something like that. For example, you have a binary um, format script that will be calling another, I don't know, binary format script, and that will be there will be, for example, calling the binary format of the elf, etc, 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 etc. Yeah, and the elf I will be talking about in the next video. So of the many formats that Linux supports, the binary format scripts is the first I want just to specifically talk about. Like, have you ever read, or I don't know, have you ever just read or written, I don't know, shebang, for example? You should look just at the shebang. You will just recognize it. This this is shebang actually, which is basically just um, a little bit that looks like bash, but it's not bash. Yeah. So not specifically that that bash, but yeah, we also, for example, um, there is a line at the start of some kind of any scripts you might see. For example, there's this little line that says, for example, um, I don't know, just a little example, dash bin, dash bash. This is a little example. So, for example, what is the story behind this line? Why do we exactly use it? So, I just always just assumed that these were handled just by the shell, but no, actually, shebang was the one who is actually a feature of the kernel and of the kernel of Linux for sure. And the scripts are executed just with the same syscall as every other program. Like, imagine just how a fact like that I've been using my whole life. I've never knew like that little line was actually just a feature of the kernel. Just the Gbang is actually a feature of the kernel that been interpreting this one. So just, I don't know. Let's take a look, for example, at this one. So when you take a look at the bin format scripts.c, you find this little line. So for example, it's saying if the file does start with a shebang, the binary formats handler then reads the interpreter path and any space separated, I think, and any space separated just like arguments just after the path, and if it stops when it hits either a new line or the end of the buffer, which is that, then 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 there is like an error that will be just thrown away. So I think this little line is just okay. But look at this the comment next, not ours to exec if we don't start with that. It means not, it's not a shebang. So like, first of all, just remember that buffer in the Linux bin param that was filled like with the first 256, which is this one. Do you remember that one? Um, Actually, that's used for the executable format detection, but the same buffer is also what shebangs are read out of and the binary format script. So during my little research, I think I just stumbled on an article. I think yes. So that describes just the buffer as 128, but at some point after just that article was published, I think the length was doubled to 256. So I was kind of curious why that happens, and I think I have stumbled upon another like GitHub um another GitHub. I think I don't remember exactly. Is it on GitHub or where exactly? But one of the few people I think have said like there is a large enterprise clients often run applications out of the networked file system where the IT mandated layout of project volumes can end up leading to paths that are longer than 128 characters, just bumping this up to the next order of 2 solves this problem in all but the most cases, while still fitting in the 500B slab. So I think this is why they have choose to use the 256 and get it to the 512 and etc. So since shebangs are handled now by the kernel and pull off from the buffer instead of loading the whole file, they are always just truncated to the length of the buffer. So apparently 5 years ago, like someone got annoyed by the kernel truncating their um, their their file, I think, or their characters paths, I think, or something like that. So their solution was to double the truncation point by doubling the buffer size. So today on your very own Linux machine, like if you have a shebang line more than 256 characters, for example, I don't know, like you're trying to do that, like imagine like it's a 256 length, then everything past the 256 characters will be completely lost. So imagine just having a bug just because of this. Imagine trying to figure out the root cause just of what's breaking your code. Just imagine how it feel discovering that the problem is deep within the Linux kernel. Um, okay, the next IT person has a massive enterprise who just discovered that was actually a genius, I think. Yeah. So the second interesting thing is that remember how it's only convention for the argument vector 0 to be the program name. How the caller can pass any argument vector they want to an exec syscall, and it will pass through just like unmoderated. So it just so happens that the binary format scripts is also the one who is also um, one of those places that assumes that the argument vector 0 is the program name, so it always removes the argument vector 0 and then adds the following to the start of the argument vector. So for example, it will be adding that to the argument vector, so it will be eliminating, so it will be deleting, not deleting, deleting is a huge word. Let's just say it will be, it's removing the argument vector for now. It's not removing it completely, but it's kind of removing. So it's removing the argument vector, and then it will be adding this. For example, it will be adding, let me remember, I think it will be adding the paths of the interpreter. It will be adding also the arguments of the interpreter. I think the arguments to the interpreter, to the interpreter. Okay, what will be happening also? It will be doing a file name of the script. What will be happening also? Yes, so this is all what's gonna happen. So for example, a kind of argument, just modification that could happen for the execve call. So let's imagine we are going to or call the execve on a function like that. So let's suppose we are having a script. I don't know, for example, a script, and we are passing, for example, I don't know, some parameters, for example, C. Uh, just an example, C, for example, D, uh, example F. Just a little example, and we are not going to pass any kind of EMVP, so let's call it just an empty array. Yeah, so this is basically just the kind of args, I think. Args or the file name, just for you to not forget those. So this is the file name, this is the argv, so, and the other one is the MVP. Yeah, So the scripts file, like for example, has the following shebang as its first line. So let's say the first shebang as the first line will be going to be like that. So it will be like that. Let's just say it's going to go from the user, just binary, mode or node. Actually, let's use node. For example, just some, I don't know, example of model. Just example of model. Some example of model. Yeah. So the modified now argument vector finally can be passed like that. So the modified can be passed as something like that. So you can find just user. So user bin node, for example. Um, we can also just the other one, which is the other string, which is um, some example, some example of model. Yeah, you can find that. So this is basically the modified argument vector. So this is the modified argument vector. So this is basically the modified argument vector. So after updating the argument vector, the handler now finishes the preparation of the file for execution just by setting the Linux bin param dot interrupt, which is this one. Um, where is the interrupt? Exactly. This is the variable that will be setting up to the interpreter path. In this case, the node binary that I have just tried to write for you, which is this one. So and finally, it will be just returning 0 just to indicate success if the preparation of the program is done. Otherwise, it will be throwing an error. So this is basically what is happening. So yes, so just before we end this little video, um, don't forget that an exec call will always end up in one of the two paths. It will try eventually to reach an executable binary format that it understands, perhaps after several layers of script interrupters, and just at the end try to run the code. At this point, like the old code was been replaced, or I think it will be trying to do or it will be just trying all the kind of options it has. It will exhaust all its options and return an error code to the calling program. And yes, so if you ever used Unix-like systems, you might notice that shell scripts, for example, run on terminal still execute. So if they don't have a shebang line, for example, .sh extension, you can test this out, for example, right now if you want. Just we can open up the shell, um, I don't know, for example, bash. You can just open up Linux and try that out just to see what is really happening. So, for example, we have echo. Let's just try, for example, echo. Um, for example, iron byte. I will be trying to send that to a actually a file, and then I will be trying to add the execution to that file. So the chmod is meaning changing mode is like telling the operating system that the file is executable, so you won't be able to run it otherwise. um, so I will be adding that to the file, and then I will be executing the file. So as you can see, it just run directly. So why does this shell scripts run as a shell script? So the kernel formats handlers should have no clear way like for detecting shell scripts without any um without any description. So well, it turns out that this behavior isn't part of the kernel itself. It's actually a common way is for your shell to handle a failure case. So when you execute a file using a shell, and for example, the exec syscall fails, most shells will retry executing the file as a shell script by executing a shell with the file name as the first argument. So bash will typically use itself as this interpreter For example, while the Z, I think ZSH, is it the ZSH? I don't remember exactly. Is it the ZSH? I think the ZSH, yeah. The ZSH will actually use while the ZSH, for example, uses this SH2, but is usually the Bourne shell. So it's a kind of another shell. So yeah, so this is basically all about the execution of a program. So one thing to remember there is a syscall called execve. You don't have to understand the whole details or a lot of details about what is happening in the kernel code, but okay, at least you have an understood of what is happening when you try to execute a file. So don't remember this diagram, it might help you. So when you run a binary, you actually call the execve that will be calling the binary, and the execve will be itself is going to do a syscall for you that will be loading and setuping the binary, and it's going to jump to the operating system code, and then it will be trying to figure out the binary format of your program. If it's figured out, then everything is okay. It will be loading the process into RAM, and then it will eventually um, start executing the program for you. So yes, so I think we hit the end of the video. So if you have any kind of question, don't forget to write in the comments sections, and don't forget to subscribe, and bye.